pretty daunting to be the first speaker up because after this point, there's usually nowhere to go but the top, right? I spent some time thinking about what I was going to talk to you about, and I realized that from the standpoint of technological advances or any of those things, there's really nothing I can say that will surprise you, right? I'm not Sundar Pichai. I'm not going to talk about conversational interfaces that will blow your mind. So I don't have anything like that to pull out of a hat. So I said, why not go to the other end of the spectrum and unsurprise you, right? So there's nothing I'm going to talk about that's going to be in the least bit surprising, but my hope is that a fair bit of it will resonate with you from experiences in your own career. Okay. Now I picked a fairly technical term for the talk. I call it gradient descent, but there's a reason why I did that. One of the things that happens as we go through life in general, I hate to get philosophical at 9:30, but there you have it, is that we learn from our experiences, and these experiences end up giving us a sort of alphabet for how we tackle the rest of it. We find shortcuts to describe what we experience from things that we've learned, things that we do. And I find gradient descent especially apropos that way, because mathematically speaking, it's about saying, okay, I'm making a mistake here. What do I do to make fewer mistakes, right? And move in that direction. So minus all the first derivative and second derivative skullduggery, that's really what it is. And I find that a very useful metaphor for our own journey as data scientists. That we end up learning from experience. As somebody put it, good judgment comes from experience and experience comes from bad judgment. So this, in some sense, is a chronicle of bad judgment. And like we do a lot of things these days, I kind of crowdsourced the talk. So I spoke to a lot of people I know who've been data scientists for many years, and I asked them, what's the one major lesson you learned that you wish you had known starting out? What's that one thing that really hit you hard, and what you learned usually by getting it wrong, right? And what I've put down here is essentially that list of lessons. It's not comprehensive. There are going to be 15 others that you can think of that are not on this list. But these are things that resonated with me, right? And because we're all technologists in some form or shape out here, I've found slightly complex ways of saying very simple things, because that's kind of how we make a living, isn't it? Right? So here goes. All right, how does this work? Okay. So Enron, right, has the motto, ask why. And in some sense, it's probably the most important lesson that I've learned, and that I've heard many people repeat to me, saying, listen, we get into these problems without really knowing why we're solving it. We look at data and we charge in with an algorithm without really knowing why we're using this algorithm. We say, oh, we need to use AI, we need to use deep learning, without really knowing why we need to use it, right? So most of the time, we don't end up asking why until too late. And in some sense, that's probably the most important lesson to learn. Okay, and it's interesting that Enron had that as its motto. It's there in their logo. Okay, ideally, auditors around Enron should have been asking how did they do all of that, but there you have it, right? So ask why is probably one of the most important lessons I can think of. And there are multiple examples of how this matters. Simple things like, oh, I have data that's missing. How do I fix this? We don't step back a lot of the time and ask, why is it missing? We're building a very complex model to put into place, and we're not stepping back and asking ourselves, why am I building this model? What decision am I enabling? I'm not building it because I'm bored. I'm building it because I have decisions to make. So am I building the right model for the right decision? What am I doing, right? So we don't end up asking it too often, right? And then we find out later that we should have. So in some sense, this is probably the most important lesson I learned. So when I thought of starting this, I realized that this was absolutely the first thing I'd put up. Okay. So the why matters. So it's usually why, then what, then how, right? But then you find this happening, right? So most of you must have heard of Edward Deming and probably what is his most famous quote today, which is, in God we trust, everybody else must bring data. Which seems to sort of imply that data drives a lot of decision making, which is true and not so much as well. That in some sense, everything we do, even our intuition, is usually informed by data that kind of got processed at some level and internalized. But the fact is that even today, a lot of major decisions are not necessarily made with data. They're not made simply because you put a model out there with results out there and then people believed you and then they went on to make decisions, right? So, I mean, I'm sure a lot of you have encountered this. So we very often find that people go by their gut or they distrust complex models and so on. So what happens a lot of the time is that however well we build our models, the who really matters. Being able to convince somebody who actually has to pull the trigger on a decision based on that model is significantly important, right? And different people have different motivations for trusting in data, not trusting in data, trusting in models, not trusting in models. So it becomes very critical to understand whom you're talking to, right? So I've had this happen to me. I'm sure a lot of you have had this happen to you, right? That the last mile is actually convincing some guy to use a great model that you've built. And if you're not able to do that, then what we've really done is build a really shiny toy that nobody wants to play with, right? And that's happened to me more often than I can count. And I know it's happened to a lot of other people I know, and probably to a lot of people in this room. So in some sense, the who really matters, right? So what this means for us is we need to teach. Oh man. There we go. Okay. Right? So we're all technologists, but a lot of the time we end up having to be evangelists. We end up having to sit down and actually teach people, right? And it becomes critical. It becomes critical to actually educate people on the stuff we do. And it becomes critical to educate them in their language, right? So the thing I realized, and I'm going to occasionally paper these with anecdotes, okay? Mostly because I find data to be a good way of getting away from making decisions. So the thing that happens is, I had a meeting with people in the energy business once, and I ended up showing them a neural network model that did something to solve a problem, and essentially it went as disastrously I could have ever hoped. And the reason was that there wasn't a single slide that spoke about things like enthalpy and temperature and pressure in ways that they would understand. And meeting got over, I came back and I said, okay, this is going nowhere. And then my colleague sat me down and he said, you might as well have been speaking in Sanskrit. Find a way to speak to the guy in his language. Use his jargon. And that makes a difference. So we started doing that. And I started spending time actually sitting down with him, sort of unpacking the model and explaining to him what I do, how these models work, and what kinds of things they sort of encapsulate in their guts. And over time, we could actually bring people around to our way of thinking, right? So a lot of the time, the who matters, but it becomes our responsibility to bring them along. That our job is not as people who build models, it is as educators. And it is something that we cannot escape. And at every level, this holds true. All right, this is usually the slide headline that gets people to pull out their pitchforks and want to burn me at the stake, right? And the reason why I put this is this, that I use the Harry Potter analogy very often when I'm teaching machine learning anywhere. That there's a line in, I think, book 2 of Harry Potter where there's a character who tells his daughter, never trust a magical object if you don't know where it keeps its brain. Which I find encapsulates popular thinking about AI and machine learning very often, very well. Because very often, so there are people who are very gung-ho about this because they believe that it's the answer to all their problems, which I think is somewhat inaccurate as well. And there are also a lot of people who say, listen, this is a black box. You might as well be slaughtering a goat in your backyard. I have no idea what you're doing, right? That happens. So people think, listen, this is a black box, I can't use it. And then what happens is they go exactly to the other end of the spectrum where they say, give me a very simple linear model where I know exactly what's going in. Okay. It's not necessary that it's one or the other. The world isn't binary. There are actually 50 shades of gray in between those black and white. Okay. Some people don't necessarily want everything to be transparent. They just want the model's results to be transparent. Right? So there's a case where we built a machine learning system to help radiologists diagnose whether or not coal miners had some form of lung disease. It's called pneumoconiosis, right? So we were trying to do this, and we started off building a model where we just labeled a chest X-ray as saying, you know, this guy has a problem, this guy doesn't have a problem. And I said, this won't do. And we realized that what we needed to do was essentially annotate that image and say, here are regions that we find suspicious that are leading us to the conclusion. They were okay with us putting a very complex model in the background, but the result had to be transparent to them. Right? In some cases, people say, listen, I don't necessarily care what functional form you use. Just tell me what kind of features you're putting into your model. Just walk me through your feature engineering, and as long as I'm on board with that, I'll take your word for the math that you apply after that. There are cases where people are just asking you questions like, is variable 1 more important than variable 2? Is age more important than income when I'm figuring out credit ratings for people? They don't necessarily want to know if you used a support vector machine or a random forest or whatever. They might just want to know, is this feature more important than this other feature? Are you doing your due diligence? Right? So it's not necessary that it's got to be an extraordinarily simple and transparent model. When people say they don't trust something that is very mysterious and complex, they don't all mean the same thing. And it's important to sort of understand what that necessity is and just address that. It's not always build a complex model or build something extraordinarily simple. There's a whole spectrum in between. Okay, I need to first mention attribution. The code is not mine, although I'd love for it to be. It's by a guy called George Box, among the great statisticians of all time. So this I find very interesting because sometimes we need to figure out if we're building the right model, right? And then we got to figure out, are we doing it right enough? Okay, so here's something that happened to me. So my first year as a data scientist, I had to build a model that got not a great result to begin with. And then I spent a whole night working on a fairly complex machine learning model that would improve it. So the next morning, my manager walks in, he sees that I'm wearing the same clothes as I did the earlier day, and he asked me, did I get any sleep? I said, no, I was building this model, and this is how far I got. So I said, okay, now here's what I want you to do. I want you to first go home, take a shower, get some sleep, come back, and here's what I want you to do. By tomorrow, tell me what the financial impact of this improvement was. Okay, so I did the calculation. It was very interesting to do something like that. Okay, so I did all of that, and then he walked me through what my hourly rate as an employee was, and he said, whatever you've done, whatever I've spent in just paying your salary for the work you did over the last day is more than whatever gains you got from your model. Okay, so sometimes you got to realize that you don't necessarily need to go all the way. You got to understand when the marginal utility starts becoming not so great. Right? So it's not necessary that your models have to be great all the time. Right? Sometimes you could build a bad model, but you could make a great decision with it. Sometimes granularity matters. So there are instances where, for instance, you want to figure out what's wrong with a piece of equipment. And the action after that is maybe to open a certain section of the equipment and inspect it. So this happened when we were doing something with aircraft engines, where we were trying to predict faults on an engine, and we said it could be one of these faults. And we were a little worried about the precision of whether or not we could get those right. But the fact is that as long as we got it down to one of some 5 different faults, they were going to do the same thing after that, which is open up a particular section of an aircraft engine and inspect it. That was a granularity of the decision. So it didn't really matter if I got exactly which fault it was. If I spent most of my time figuring out whether it was fault 1, 2, 3, 4 or 5, I was wasting my time. As long as I narrowed it down to just that set, my decision at the end of the day was going to be the same. So I would have still made a good decision with what on the surface would have looked like a bad model, but actually wasn't. Okay. But this whole question of what's useful also brings to the point of accuracy. Let's think about chatbots, which are very popular these days, right? For a lot of people, when they think AI, they think chatbots, they think conversational interfaces, right? So think of chatbots for a moment. A lot of work that goes into figuring out how a chatbot works is when somebody types in a question, you want to figure out what the intent of that question is, right? You're spending a lot of time on intent identification. Imagine how much easier this problem would get if rather than solving the intent identification problem to the ends of the earth, you were solving the autocomplete problem. Think of how Google search works. How often do you actually type in a whole search phrase? 2 words in, Google has already told you what the remaining words are. So most of the time, you're just clicking on whatever is the closest match to the thing you wanted to ask. Think of how much difference that might make to chatbots. Think of how much difference it would make if you just put up a list of most popular questions by saying, what do you want to do today? And then you made it adaptive and so on and so forth. If you solve that problem, sometimes you don't necessarily have to solve the intent problem. You don't have to worry about language and grammar and so on. You've made your user's job simpler and you've made your own job simpler. So that's what I mean about doing the right thing. You don't necessarily have to solve that complex problem out there. Sometimes you have to solve a different problem that just makes everybody's life much easier. Right? So do the right thing and then do it right enough to count. Right? This is important. Right? So we keep talking about complex models, and these days we increasingly talk about complex models. But the thing to realize is there is no free lunch. Right? Now, there's a whole mathematical interpretation to this. There are things called no free lunch theorems that say that right off the bat you don't know which method would work best for a problem. That's a question that's commonly asked by data scientists, right? So what algorithm do I throw at this problem? Do I throw random forest? Do I throw logistic regression? Do I throw support vector machines? The answer is I can more or less guarantee sitting here that I don't know the answer, right? So that's the truth. That's the mathematical interpretation, but there are multiple ways of thinking about all of this. One of which is, okay, I think we just moved a slide ahead. Yeah, that complexity comes with a price, right? When I say complexity comes with a price, think about this. That when you build a very complex model, you have to pay for it. Okay, from a modeling standpoint, there are only two currencies that the universe generally accepts in return for giving you complexity. It will either accept data, and a lot of it, or it will accept domain knowledge. Those are the two currencies that you can offer in exchange for getting complexity. And this is not even considering the amount of technical debt you are incurring in building a complex model and making it live inside a large ecosystem. Okay. One of the wisest papers I've seen to have come out of Google is a paper that talks about the hidden technical debt of machine learning models. Okay. It doesn't talk about great advances in machine learning, it talks about how difficult it is to actually make any of these models live. Okay. And there's a whole bunch of things that you have to do right around a model to the point where you realize that the modeling algorithm you use or the AI you put in, whatever, is the least important thing about that system. Everything else counts. That you might have replaced with a guy sitting there and producing random numbers and it would probably still be okay. Right? So complexity comes with a price. But that doesn't necessarily mean that you have to pay it in full. There are ways of paying it that are nice, such as, for instance, the ability to learn from what other people have done, right? There's a whole concept called transfer learning that's very popular these days in AI. So think about this, that supposing I wanted to build an algorithm that would recognize in a photograph whether or not there's a human being standing there, right? And let's say you took photographs of me, and I'm human, more or less, right? And you're taking these photographs and you're trying to figure out whether or not there's a human being standing there. And then you want to build an algorithm to figure out whether or not there's a chair in the picture. The fact is that most of the things you need to do to find a human being are the same things you need to do to find a chair, which is stuff like, I need to see if there are edges in an image and objects in an image and so on, and then you need to figure out what exactly you're solving, which means that a lot of this complexity that you need to pay for, you've already paid for on a different problem, you can pretty much transport it, right? So figure out where you can actually pay it easily, where you've already prepaid it elsewhere and you can just carry over those credits. But remember always that complexity comes with a price. There is no free lunch. Right? Oh man. That brings us to the aspect of crowdsourcing. Right? So here's what I realized. So when we talk about Netflix, we talk about how it upended the blockbuster rental model. We talk about how it revolutionized streaming media and so on. But for the people in this room, the biggest thing that Netflix did was kickstart the crowdsourcing revolution. Pretty much every component that went into it existed before that time. None of this is new. When Netflix came up with the Netflix prize and said, listen, build me a great recommender engine, and they threw it open to the world, everything that in some sense conspired to make that particular contest a success existed already, right? Maybe the algorithms, some of the algorithms were new, but think about it. There was always the open source movement for a very long time. People like Richard Stallman had written wonderful articles like The Cathedral and the Bazaar about how people need to share their knowledge, share code, share data, and so on. So none of this was new. It's just that at that point, it created a perfect storm of circumstances so that that price became, in some sense, the standard bearer for how people across the world could collaborate on particular problems, right? So what it means is that when we talk about complexity and we talk about, you need data and you need this and so on and so forth, one of the things we forget is that it's not always a guns and butter choice. It's possible to actually import knowledge from elsewhere, and crowdsourcing is a very big part of how you end up doing that. So if you can do that well, then what happens is that you can build great models simply by potentially opening up your problem to a larger group, or by considering the fact that what other people have done can be used to great benefit in your own problem, right? So as Newton said, I see further because I stand on the shoulders of giants. And that's pretty much what makes a huge difference today. In some sense, I would say that the reason why we're talking about AI so much, and the reason why a lot of very complex models have become sort of ubiquitous today, is because of this. It's because people are beginning to share models and share data a lot more, right? And it's a fact that's not gone unnoticed by the traditional statistician community either. So there's a statistician called Leo Breiman, who's best known for random forest, for instance, who wrote a lovely paper on the two statistics. So he talked about how there was a traditional way of doing statistics, which had to do with coming up with very robust theoretical results and publishing it in journals and so on, but also the slightly newer school of statistics, which involved a more practitioner's viewpoint, where you'd build something and you'd put it out there in conferences, and other people would look at it and they'd do their own thing, and you'd keep doing it again and again, right? It's a lovely concept, and in some sense, what he's talking about is how machine learning is transforming that. When you look at machine learning itself, or AI right now, its parents are computer science and statistics, right? So in some sense, this whole business of people collaborating and working very, very fast is making a huge difference. And it's what's really driving this field, right? And if you're doing that, here's the thing we need to realize, right? That in the time that I took to give this talk, which is what, 20 minutes now? Less, maybe? In the time that I took to give this talk, there have already been 10 papers published somewhere that expand our conception of what's possible. By the time we're done, there'll be 100 more. Okay. It's not like Alice in Wonderland where you can run as fast as you can and still stay in the same place. You run as fast as you can, you're still going to lag behind. Okay. I hate to break the bad news to you early in the morning, but that's really what this world is like right now. Right? Things move incredibly fast. So at some point, it becomes very easy to say, okay, I give up, I can't learn anymore. I can't figure this out anymore. Right? And that's really not an answer, right? So the key then becomes, can I learn to learn? How do I figure out how to keep pace with this? And the thing that keeps coming back to me is something that my thesis advisor once told me. So here's what happened. I had to teach a course on data structures. And I went to him and I said, listen, I have to teach data structures to a bunch of guys. And I know the subject. I know all these algorithms. I know all these data structures. I just don't know how to teach it. Then he sat me down and he gave me maybe a 20-minute spiel that really rocked my world. He said, every data structure you look at is an answer to the question. Every paper you read is an answer to a question. You don't worry about what the answer is. You don't try and memorize the answer. You try and understand what the question is. So you start off with arrays, you were doing something. Then you added trees because there was something you weren't able to do well and you wanted to do it. So that was the question that trees were answering. And then some other method came along that answered a different question that trees weren't able to answer. So everything now sort of organically fit into a much larger picture where it just became an answer to the next question. So when we encounter all this complexity and all these great models that we start seeing, the thing to ask ourselves is, what question does it answer? Right? So then what happens is, everything we end up learning just becomes an organic part of whatever we already knew. Right? It just becomes one more question for which this ends up being the answer. And it becomes a lot easier to assimilate. And I found that it was probably the most useful lesson that he could impart to me in my entire research career. Which brings us back to how we think about learning, right? Every little thing we learn, and I'm sure we learn a lot today from all the great speakers out here, right? It's going to be one more little thing that we learn. It's going to be one more step in our direction to becoming better data scientists, better analytics professionals. And in some ways, what we're all going to be doing today and for the rest of our careers and lives is gradient descent. Thank you.